So every year I try to pick a title for a talk that's like just good enough to get accepted, but not good enough to have like the big room or something like that. Kind of get the small out of the way room behind all the vendor booths. I think I did okay, but you guys, good turnout, so thanks for showing up. This is about multi-label classification with Scikit-learn. I'm Chris Finn. I'm a senior principal architect, distinguished engineer in Cerner's medical informatics group. I'll tell you a little story today. This is more as much a post-mortem as anything else, so I'll get a little bit into the nuts and bolts. A lot of years in the past with my DevCon talks, I've been more kind of aspirational, call to action, a little bit softer stuff. So I try to do a little bit more nuts and bolts here. This isn't going to get down into, I think there's one later today that Brandon Weaver was showing me how he had show term IO and everything blasting out through the terminal and stuff like that. I'm not going to get that into that level for this, but I will show you a little bit of code. So every good story has a quest. So the quest for this talk is to build an algorithm to correctly tag Stack Exchange questions. I want to be able to do it. I'm going to self-impose some constraints on this too. So I want to be able to do it on my laptop, be able to train and classify everything to make these predictions, and do that in less than a business day. And as part of this project, I also wanted to learn a little bit about Scikit-learn. So it's always good to have something in your tool belt, and then score respectably in a competition where this problem came from. Why would I want to do this? Okay, so Cerner's awash in free text data. There's a lot of unstructured text, chart search, crawls, all the documents from 150 or so clients. There's a lot of knowledge that's contained in that text, but it's not really easy to get at. And there's a lot of things we want to do with that text. We want to summarize it so that it's easier to navigate. We've indexed it so you can search and find things in it. We want to find relationships between things within that, between concepts within that. And being able to understand how to work with text at scale and learn from it is one of the things I wanted to take a look at. Yeah, and then, like I mentioned, add techniques to the tool belt. So the characters in this story. Scikit-learn, you can find it at scikit-learn.org. Sometimes you hear it referred to as sklearn. I'll probably go back and forth on that. And it is the toolkit that we're going to use to show some of these different things, some of the different classes to do. Just a pretty simple problem. It's actually a complex problem, but I'll take you through the story on that. And then it rides in on the trusty steed, which is this early 2001 MacBook Pro with 16 gig of RAM. I kind of cheated, bought some off Dave Olarte and put it in. Okay, so Scikit-learn. How many people here work in Python or use it routinely? Okay, good. So Scikit-learn is a Python-based toolkit, and has anybody used that before? Used it? Did you work on the solution work thing or something? Somebody had something where they did some classification? No? Okay. I taught a course a couple weeks ago, and there was somebody that actually, I think, had used something similar to that for a problem in Cerner, so I was kind of excited about that. Okay, it's a Python-based toolkit. It's built atop NumPy, SciPy, and Matplotlib. It has tools for a whole bunch of different machine learning purposes, so it's a machine learning toolkit. But it's not just about the machine learning algorithms, it's all the things around it you need to do development. So it can do things like classification, regression algorithms, clustering, but it also helps you with data preparation and doing things like feature extraction, like how do we go in and take this unstructured data or this data that needs to be manipulated and extract useful features for some of these algorithms out of it. There's toolkits in it for dimensionality reduction, so that's one of the problems we'll face later on in dealing with this. And then also utility toolkits for things like measurements, testing, parameter tuning, finding out how to tune these algorithms the best way. Okay, the setting. So Kaggle. Is anybody familiar with Kaggle? So a few people. Kaggle is a competitive data, it's a site that's based on the premise of competitive data science. So they host a lot of competitions. Their boast is they're the world's largest community of data scientists. And typically how they engage, or what their business model is that companies contract with them to sponsor or companies will sponsor competitions, and Kaggle kind of runs the infrastructure to handle that. So if you're a company like Cerner and you have an interesting data set that you can provide and a problem that you want, this community of the best data scientists in the world to go take a look at, and you can host that data set there, define the rules of the competition, and they manage all the infrastructure around hosting the competition, hosting the data, doing the scoring, providing the community forums, things like that around that. And the reason that companies do this are for a variety of purposes. It could be for public relations. They just want to get their name out there. Often it's for talent identification, for recruiting purposes. But then I think some of them also do it to get another set of eyes on their problems, or have people take a look at it as a way to potentially, rather than build that capacity in-house or, see what the state of the art is let other people kind of do some of that discovery for them. So it's almost a little bit of a little less of this, but it's more of a workforce extension idea. You can compete either as an individual or as part of a team. You don't have to identify yourself. You compete anonymously. So for this challenge, I competed anonymously during that because of the nature of this particular challenge. I didn't really want to be contacted afterwards. But they have leaderboards. It's all gamified, so you get badges if you finish in the top 50% or top 10%, and it keeps track of all your competitive scores over there. The other thing I like about it is it's a way to work on these problems, and you don't have to share your intellectual property after you're done. Unless you want to collect a prize. So they have various competitions. Some of them are just for the glory of being at the top of the leaderboard. They have other ones like I can't remember the name of it. It was a hospital readmission one that had a $3 million prize associated with it. Well, if we could solve that problem, it's worth a lot more than $3 million to us. So Cerner chose not to go sponsor a team in that competition. But there's other prizes too that are, and including for this one that's coming up, a job interview with Facebook, which I didn't really want because I don't want to go work for Facebook. So anyway, the good thing about it is it gets you exposure to lots of interesting problems related to dealing with big data. And a lot of them relate back to things that we face at Cerner, problems that we have to solve. The convenient thing about it is that they provide the data sets for you to work with, and they're realistic data sets. One of the challenges in working with big data at Cerner, I think, is getting access to that data and getting it in a form that is de-identified, that you can work with, and you can go take on some of these problems realistically. And these are probably what I think are the biggest benefits of it. You get to validate the work that you're doing against, and your thinking about how to go solve problems against some of the best people in the world. So if you have a crazy idea and you think you're doing it really well, there's nothing better than being in competition with someone else to show how far behind you really are in your understanding, or to prove that you're on the right track. So there's a lot of good things from that. And they have great forums too. So the postmortems on a lot of these competitions, if you go read through them, you learn a lot of different techniques and what works well and what doesn't, and how people, but better than that, how people think about solving these types of problems. So I'll convey some of that hopefully with my talk through this particular project. So the plot. As I mentioned, this was the Facebook Challenge 3. It was a recruiting challenge. If you were in the top 3, Facebook would contact you and you could go run through a gauntlet of interviews with them. No desire to do that. What really interested me about it, though, was it had a lot of relevance to some of the work that we were doing. It had a data set that was quite a few Stack Exchange posts. So you're familiar with StackOverflow, or the whole set of Stack Exchange sites, right? There's some around very narrow programming topics. There's math ones. There's all different kinds of different topics that they brought up. These kind of vertical Stack Exchange sites. So you have the question, text, and title. Given those, predict the tags that people associated with them. So every Stack Exchange question has 1 to 5 tags associated with it that either the author puts on or the community. The community editors add to those posts to help you navigate kind of semantically through that. And then the ranking on this, so the only other constraints were you can't use outside sources. You can only use the data that they provide. So you can't go out and actually search Stack Exchange to find out what those are and bring them back, or you can't use Wikipedia to go, get some semantic hierarchy out of that to pull in. You had to just use the data that they provided. And then you're ranked on F1 score. And I'll talk about that in a minute. The amount of data, and why I wanted to kind of put this interesting little constraint on it, which was using the laptop, using Python, Scikit-learn. There's 2 million questions that are in HTML, which consist of the questions, the titles, and the labels, which have 1 to 5 per post as a training data set. There's 4 million unlabeled questions as the test set. So you have to go learn from those 2 million and then figure out how to tag those other 4 million. So there's a lot of stuff to chunk through. So your submission set then is 0 to 5 tag predictions on the 4 million test set rows. So here's an example of the training data they provide. So there's a CSV that has 4 columns in it: the ID, the title, so automatically port Zen images to EC2, the body, which is HTML, and it has all the nasty HTML markup in it, so all the escape symbol characters and all that. And then at the end, the 4th one is space delimited tags that are associated with this. So this post is tagged Amazon, EC2, and Zen. Okay, so I mentioned 2 million trained or labeled data items, 4 million test unlabeled items. We're going to predict the 4 million for our submission set. They're going to have labels associated with them. And then when we submit them to Kaggle.com, during the initial phase of the competition, they provide you feedback in the form of a test score, and the leaderboards are driven off of about 30% of the data. They don't tell you what 30% it is. They score it. You get your score back. It's only on 30% of the data. And then when they finish the competition, they get scored against the 70% that you haven't seen before. And then the other trick is they limit you to 2 submissions per day, so you can't really kind of learn which 30% that they're scoring on and try to, over-optimize or overtrain to that or do any of that. So that's to keep you from training too much on the initial test score. So you want an algorithm that's going to generalize, that applies to data that you really haven't seen before. As I mentioned, the object of the quest, get the best score. So F1 score. F1 score balances precision and recall. Precision measures whether your predictions are correct, and recall measures whether everything that should be predicted is predicted. So here's an example of precision and recall. Let's say that our right answer for the tags are A, B, C, D, and E, but our algorithm predicts A, B, and G, and X. So we got 2 right, 2 wrong, but we only predicted 2 of the 5. So our precision in this case, 2 out of our 4 are correct. So our precision is 0.5. Our recall is 0.4. We only recalled 2 out of 5. And then the F1 measure kind of balances those. So there's the math on how to calculate the F1 measure. So our F1 measure is 0.4444. And one way to have perfect recall, right, is you just return every possible tag. It could be you return everything. You're going to have a 1.0 recall. Your precision is going to be, if you get those, if you get some right, that'll be okay. But your recall will be awful, right? Because you predicted way too many, and then your precision is accurate. I got to come back to this, but we'll talk about it a little bit. So anyway, there's sklearn.metrics, which is one of the measurement packages. Calculate F1 score. So you pass in your test Y, which is the right answers, your predicted Y. So I'll talk about X and Y. So X are the features that you're given. So in this case, the X is going to be some things that we've extracted from the posts that we want to use as features. And then we're training an algorithm that's kind of a function that when applied to X produces the Y. So the Y in this case is f at X implies Y or generates Y. The Y in this case is the tags. So if you think of the test Y, those are the Ys that are the tags that we want to predict. The Y pred is the prediction, and then we have a mechanism we can use to kind of tune how the F1 score is calculated. So average equals micro. So micro has some implications. I'll talk about it a little bit. But the basic implication there is rather than not make any prediction at all, you're better off making a prediction because that will generate it'll either improve your recall or your precision or both, and that will contribute to the overall score because you're averaging your F1 scores across this entire set. So if you have a lot of zeros in there because you didn't predict, that's not going to contribute to make your F1 score go up. So you really want to have to predict something if you can. Okay, so we got the scene set, we got the players, we got everything. We're ready to start. So when you start with Scikit-learn, the best place to start is the Scikit-learn cheat sheet, okay? So with this cheat sheet, it's not actually provided as part of the toolkit. This is actually part of a blog post. You start up at the start. So this is how you kind of pick. It helps you walk through your problem, make sure you understand what kind of problem you have, how to go about solving it. So we start at the start, and the first thing we hit is, do we have greater than 50 samples? Well, of course, we got 2 million samples, so yes. Move down. What are we doing? Are we predicting a category? Yes, we are. We're predicting tags, right? You can think of those as categories that a post belongs to. We bump up a little bit. Do we have labeled data? Yeah, we have our 2 million labeled examples. We move up. Do we have less than 100,000 examples? Nope, we got more than 2 million. We move up. It recommends the stochastic gradient descent classifier. And if that isn't working, then we can move on to kernel approximation. So let's just start with the SGD classifier. And when you think about this, you really don't have to go through that. When you think about this a little bit, you realize that this is a multi-class, multi-label problem. So at multiple classes, a post could be in any number of classes or be associated with any number of tags. And then each example could be have any number of labels. In this case, we're going to constrain it to 5. The approach we're going to take is we're going to do one versus rest classifier using the SGD classifier as a way to do that. I'll show you an example of this shortly. But one constraint here is we have like 42,000 classes. So as you scan through the data initially, you look at those 2 million examples, there's 42,000 different labels in that data set. That's quite a few classifiers. Okay, so one versus rest classification real quick. The way that works is you train a classifier for each tag. So its only job in the world is to decide, is this about Amazon EC2 or not? And it comes back with a score or a coefficient that tells you or a confidence level, how confident it believes that this is about Amazon EC2. You do that for every tag that you possibly have. So that's 42,000 classifiers. What the one versus rest classifier does is it manages that. Manages running all those, doing all those training runs, keeping track of that. And the classifier that's going to use for that is the SGD classifier. And when you have all those, then you go query that classifier and ask which one is the best one, or which are the best 5, or which are the best above a certain threshold. And those would be the tags that you predict. Okay, so this is an example of, so SGD classifier is a linear classifier. It means that if you were to plot all the features of a post in a vastly multi-dimensional space, they're going to be points all over the place. We're going to try to draw a plane or a line through that separates that. Well, you can't really. That's going to be really hard, right? So it's going to be really sloppy. This is an example of where there's 3 SGD classifiers. They're trying to partition this out. And so, see, it does pretty well. Like the blue line kind of separates off the blue stuff. The yellow, there's a little bit of yellow-red mix in there or whatever. So it's not perfect. There's different confidence level as you slice that up because you're using a linear classifier. But the big advantage of a linear classifier, of SGD classifier in this case, is that it really scales up well. It's fast, it's cheap. So it's kind of cheap and dirty. You can really, it works much better. So if you go back to our decision tree, when it said we had greater than 100,000 examples, that's why it sent us that way versus more of the, some of the SVD type classifiers that are going to try to fit a curve that kind of snakes in and around all the different points and creates a clean demarcation of all that. So this is kind of cheap and dirty way of doing it, but it actually works kind of well. Okay. Here's kind of our training pipeline. So we're going to ingest the training data. We're going to build a feature vector In this case, our feature vector, our x, is we're going to replicate the text of the title 3 times, just on the intuition that usually the title of a document or the title of a post conveys a lot of important information. It may have a really close association with the tags. We're going to include the body, and then we're going to break up those tags since we know what they are. And we're going to kind of seed those in as features too, as just kind of hints to amplify. If those words appear in the document, they're going to show up a little bit more. Then our y is just the tags that were predicted. We're going to do tf-idf vectorizer on that. So we're going to take this bag of words that we have, that we've concatenated together in a big string for our x. We're going to turn that into a numeric vector that represents the importance of those words within the document relative to the whole corpus. What that ends up giving us is a matrix of, in this case, let's just say that we're going to train on 200,000 examples. I'm sorry, 100,000 training examples, and we have 200,000 features. That's how big our tf-idf vectorizer is. We're going to train on that, and we're going to fit that with this one versus rest classifier. And then we're going to pickle the classifier and vectorizer to save for later on when we do our prediction, which is kind of an expensive operation. As I don't have the numbers on here, but there were times where I did these big training runs where I'd have like let's say like a file that couldn't be backed up by connected network backup because it was over 16 gig or something. So pretty nasty stuff. So when we predict, we kind of do the same thing. We ingest the test data, we build the feature vector exactly the same way as we did before. We don't have any tags because that's what we're going to predict. We load and fit the tf-idf vectorizer. We're going to have 4 million by 100K sparse float or matrix. We're going to load the classifier. We're going to fit our x to that. We're going to apply the classifier to it, and that's going to kick out all our tags. So in code, just look at the middle for right now. One versus rest classifier takes as a parameter, as part of the constructor, the SGD classifier. You have different parameters you can set on that. If you look at the top example of parameters, there's something called like a CV grid search, which is a way of, if you want to figure out what the right parameters are, but you don't want to run all the tests yourself, you just specify, I want to try every combination of all these, and it'll go train a whole bunch of different things and tell you what the best ones are. So anyway, these were some examples of parameters I found that work pretty well when you want to go to predict. So if you look over, that's the end of that constructor is the .fit. We're going to give it the features and the labels, and it's going to learn the classifier from that. It's going to build the internal 42,000 classifiers. When we go to predict, we're going to give it the test data, and it's going to kick out the labels in our Y prediction. Okay, so can anybody hear like the train coming? There's a train coming. Okay. I don't know. Anyway, curse of dimensionality. So we have 42,000 classifiers. We have 2 million training examples. We got 250 to 1 million features if you think of all the unique words in that document that have to be turned into by the tf-idf vectorizer. My MacBook Pro says yikes. So we got this guy going. There's my MacBook Pro. That goes on for a while, but getting kind of short of time here, so we'll move on. And so I thought, let's take the road less traveled, right? There's got to be something more creative way to solve this. So sometimes there's a reason you don't want to like build your house on the road less traveled because it might be like a train track. But anyway, so a couple flawed ideas here. I thought I'd do some clustering. So I had this intuition that posts about similar topics are going to cluster together. And rather than train this big classifier on every possible post, what if I just clustered all these posts into clusters, like 400, 500 clusters, and then learned a faster classifier on each one. Maybe it has to learn fewer tags, do some of that, save a little bit of processing time, possibly not eat up as much memory. So I used the mini batch k-means classifier. I think I did like 450. I tried different variations on that. And what that kicks out is for your test set, it tells which cluster each post belongs to. Okay. So you get this array, and it has all your posts in it, and it just says, this is in cluster 1, this is cluster 450. Turns out this was a dumb idea. It was slower, no real gain in accuracy. Each one had several hundred to 1,000 tags each, so it was quite a bit faster to train each individual one, but I had to train 450 separate classifiers. And plus, it had this expensive singular value decomposition step in it, which costs a lot of time. And the clusters were kind of uneven. Some of them you could predict really well. Other ones were just kind of this whole thing you'd look at, and you just think, okay, yeah, that's about computers. I mean, it's just, there's no real theme to some of those clusters. Well, that was like, cooking my desktop. I got thinking about taking a non-machine language approach. I looked in the past at something called index learning, where you associate keywords in the titles back to the tags that are associated with that, with the thought that if you can find those kind of co-references of those co-occurrences, you can kind of go back and use that in reverse to predict what tags might be associated with words that you see in there. It actually wasn't kind of a bad idea. It ended up being a poor implementation. So an example would be how to get user ID when user accepts the request Facebook app requests. And that was tagged with Facebook Graph API, app request. So I decomposed the tags. I removed the hyphens, used those components, and then used the counter, the Python counter of the parent tag to associate that to the keyword in anytime there was a match between something in the title and the tag, I'd keep a count of that. And then I'd run that over the whole thing. So it ran okay, decent speed. I'd go through and count all those up. And then when I'd apply it, I'd just scan through and look at my hash and find what are the things with the highest count, and then use that as a prediction. So very crude approach, but I was kind of trying to figure out something to do when I was scratching my head on these long clustering runs. Still scored 0.27, so clustering would get me in the 0.30 range, and I'll tell you where that kind of fits in later on when you take a look at the overall competition. This isn't very good, but this did okay for not really even using Scikit-learn. And it turns out the winner took a similar approach, but had much more solid mathematical foundation behind it that actually made theoretical sense, other than my crude attempt. So anyway, I'm trying to be too smart here, right? And I'm trying to optimize too early. What I should have done instead was focus on reducing the dimensions with the tf-idf vectorizer and tweaking that. TfidfVectorizer, and this is probably the biggest thing I learned about dealing with text. It's a very simple approach to feature engineering, and it has such great features on it that you can really get a lot of improvement quickly if you can figure out how to tune it. So let's let that do the heavy lifting. So term frequency and inverse document frequency, here's the Wikipedia definition. It's a numerical statistic that's intended to reflect how important a word is to a document in a collection or corpus. So if the word occurs frequently in a document, it's probably pretty important, especially if that's the only document or one of the few documents that has that word in it a lot, as opposed to if it's very frequent, but it's frequent in every other document, it's not gonna be that important. So this is a way of kind of weighting the different things, the different words in our bag of words, to give them a sense of what's important. Okay. So tf-idf-vectorizer, this is what you create at the top of, after you've ingested your data, you're going to create this. Couple of important parameters here. Max features, 200,000. I can actually set the dimensions that I want to fit this into. The minimum degree of freedom, that says I don't really care about things that are very, very rare. They just take up space, right? They just add to the end. So that's basically saying 0.09%. If it's not in 0.09% of the documents, just ignore it, throw it out. What this really does is it makes the training runs go a lot faster because you're guaranteed you have a fixed size of how long that feature vector is. You don't really have to do a lot of the, you don't have to be smart about picking what those features are. It's going to pick the ones that are most relevant. And then the real trick there is the n-gram range of 1 to 3. So when you apply the vectorizer, you fit a transform on your training examples, and you do it also on your test examples. Okay, so I mentioned ngram. Say you have a body text with the phrase Windows XP crashed. Ngram of 1 to 3 will produce 6 features. It'll go through and it'll break things into unigrams, bigrams, trigrams. So it'll come up with Windows XP crashed, XP crashed, crashed. Okay, those will all be features that we're going to learn on. And you can start to see that some of the semantic meaning is preserved in that. And if that occurs again and again and again, you get some higher level concepts that sort of start to correspond to tags. So we're going to find broader variation. Okay. It turns out there's no gain by going up to quadgrams. So 1.4 doesn't work. 1.2 isn't quite as good. 1.3 actually worked out very well. As soon as I did that, my scores immediately went up to 0.3924. This was just training on 90,000 examples and then the top 7,500 tags. Okay, so there's something that's weird though. So everybody's submitting their things and they look at the literature, and the literature says if you do best practices, you should be able to get 0.5 to 0.55. There's some people on the leaderboard that have 0.79. Like, what's going on here? It doesn't make any sense. It's like, are they cheating? But you look at their bios, and they're pretty honest people. So what it turns out is that there's some overlap. Some of the training examples were provided in the test data, and there's kind of some hand waving of, oh, that was part of the point, but I think it might have just been a screw up. If all you did was recognize that those were in the training example in the test when you submitted, you get a 0.583. If all you did is just duplicate those tags, you get that. So everybody wakes up one weekend, and it's like, oh my gosh, there's a new baseline. Okay, we don't even have to do anything with those. We just copy those over and we start from there. So you only have to predict on the non-duplicate rows. Lesson there, don't forget your upfront data analysis. There may be some patterns in the data that you missed that give you some easy gains. Okay, so I got my first one versus rest classifier. I'm going to build a second one. More feature engineering. David McCauley was kind of working on the same project at the same time as we were exploring this. So we created some synthetic features to roll up synonyms. By taking this approach, prior to tf-idf vectorization, this got 0.417. So I went from 0.39 to 0.417, and that got me up to 0.758 on the new baseline. I'm kind of running out of time here, so I'll skip over this real quick. So basically, this is just replacing some phrases with features to overcome tokenization issues. As I mentioned before, ngrams did a little bit of this. But this showed some improvement because it constrained the dimensions to allow us to go farther into less frequent tags, which kind of started picking up the tail of these tags. If you look at the distribution of the tags, there's a lot of stuff about JavaScript, C#, you can predict Java, Python, PHP. But as you go down, it becomes very obscure, like particular versions of things. So here's an example. One cool thing you can do with a tf-idf vectorizer is you can print the features that it recognizes. So here's some excerpts from the ngram one. So you can see how macOS, macOS 10, macOS line, those are all kind of talking about the same thing. Those are words that appear in documents frequently. Those are candidates to roll up into a single concept or a single feature rather than have those take up extra slots. Okay, so this is just a quick replace. I went through the documents before I processed them, and I had a table of about 100 of these that I'd replace. Okay, so putting it all together, classifiers aren't going to predict on every test item. So some it just doesn't know. There's nothing above a certain confidence level. You're always better predicting something rather than nothing to get if you want to get a better F1 score. So what I ended up doing was stacking these classifiers in a way. So we're going to combine multiple methods to get the best prediction. I didn't do any weighting in this. I kind of played around with it a little bit, but I just said we're going to go with our best classifier first, second best classifier next, so on. So this is basically 10 prediction files that got merged together. First thing we do, we get our cheap and easy stuff, the 0.583, the duplicates. Then we get a consensus on our two different one versus rest classifiers. And I did reuse some of that clustering stuff, so there were still some posts that can be used. I clustered those against known posts and then had 5 little classifiers that would say what's most likely to be associated with those. Not really a big gain there. And then the default, so the 5 most common tags are JavaScript, C#, Python, PHP, Java. If you couldn't find anything else, just throw it at the wall and see if there's a chance you're going to be right. So if you look at when we stack these, dupes, 0.583 baseline. When we add the consensus of the 2-1 versus rest classifiers, we got to 0.76. We had the index learning approach, 0.765. Did the cluster prediction, got another 300ths. And then the default predict, got another 300ths. Big question, did we generalize? So after the competition closes, as I mentioned, you're scored on the 70% private data. If you generalize, the score shouldn't be that much different. So before, that's actually should be 7701. Got that wrong. No, that's actually right. After 77091, which is pretty good. So it did generalize. It didn't fall off the face of the earth when we tried it with those 70K that it hadn't seen before. If you want to kind of put this in terms of where you are on the leaderboard, so we want to compare ourselves to others, just doing duplicates got you 46%. So like 46% of the people didn't even read the forums and kind of figure that out. 1 versus rest consensus, that was enough to bump up to the 86th. You add in all those other predictions, that was enough to get to the 89th. So I ended up 41st overall with my anonymous entry. Winner score was 0.813, so they got a little bit of boost after that was discovered. I mean, they kept working versus 7791. It looks pretty close, but it actually isn't. So when you take out the dupes, 0.552 is basically what the leaders got, which is kind of near what the literature says the theoretical max should be, and versus 451, which is what the contribution of the work I did there was. So there's still quite a ways to go. This isn't like a glaring success, but it shows kind of how hard it is to be, at the top versus, all the mistakes you can make along the way when you don't know what you're doing. So the lessons: pre-analyze the data, reality check against the literature, other competitors, avoid premature optimization. That cost me a lot of time and CPU lifetime. Save the innovation and complexity until you have a great baseline score. So do the dumb things first. Follow the cheat sheet. Jack around with the tf-idf. There's a lot of knowledge in Scikit-learn that you can leverage. You have to do a little bit of reading. You got to read some of the literature to figure out how to tune that stuff. But that's really great. You can use that grid search approach to do that. I think, I did a lot of those extra things that were really diminishing returns. They didn't really improve it from 0.75 to 0.77. Not a big deal in the real world. It's only worth doing that if you're like chasing, your competitors. So the winner solution was developed on a 256 gig machine. This guy had access to quite a sweet machine there, but was able to squeeze it down so it only ran when he finished on a 64 gig RAM machine. And the leaders were using like associative approaches, lots of hand tuning, lots of things that don't necessarily apply. You kind of come in with this custom solution. So any questions? Sorry, I kind of ran out of time here, but yeah. So the question was, what do I think of Scikit-learn versus Weka, which is like a more Java-based, right? I like it primarily for the documentation that's in Python. So I think it's like, to me, it's more easy to experiment with. I know there's some there's some algorithmic approaches you can use with Weka to help you find what, you can run a whole bunch of different things at once. So if you don't know what your problem is, it can kind of steer you towards, it's kind of got the cheat sheet sort of built in if you want to throw processing power at it. But I kind of like this just from the standpoint of like in Python. And it's just, there's so much other power with NumPy and SciPy and sparse arrays and things like that I've kind of moved on from Java and like the Python better for data science stuff. So, yeah. I'm sorry, I didn't catch the. Right. So there were a couple linguistic things in there. Oh, so the question was, did I use any linguistic approaches, or why did I consider that as opposed to just hammering away at it as a math problem? Right. So the tf-idf vectorizer has a few things in it that start to get into that. One thing is you can exclude English stop words. So there's a stop word list in NLTK that I think's incorporated back into Scikit-learn. So that cuts out some of it. So that's a little bit of understanding of the core language. When I did the synonym work, there are a lot of symbols and stuff like that that get parsed. So if you see the greater than, you get the @GT semicolon, right, because it's HTML code. Those are things that I would go replace with higher level tokens so they get tokenized differently. Like I said, I didn't do a lot of the trying to understand just because of understand meaning of the individual posts from more of like an NLP perspective. The reason I didn't do that was because there's just so much data, right? There, and it's so spread out. There's 42,000 tags, right? 2 million posts. So computationally, I think when you get with data this big, you really have to, you got to take some shortcuts. So that kind of limits what you do. But there were a little, like understanding the synonyms and the tokenization. There's things like that where you can build some vocabularies or custom vocabularies. So I think that's interesting to look at because with the tf-idf vectorizer, you can provide your own vocabulary for it. So you can start looking for patterns within that text that you want to be represented in that. But I didn't consider that beyond those. So. Okay, we're like 1 minute over. So Hypnotoad says fill out your card. As Amber had pointed out, one of the things, they got them backwards on the card. The number line is supposed to go from left to right, but on the cards it's right to left. So anyway, that's why Hypnotoad's there to tell you to look at the +1 or whatever you want. He can move around. So, all right, thanks.